Now, let us get back to the presentation. So, using this intensifier MCP, something that is a little more sophisticated than just ICCD is often used, and that is called a streak camera. It sounds strange. Camera we understand now, because we have talked about CCD camera already. What is a streak camera? What is a streak? We will see very soon. But to do that, once again, let me draw something before we start presenting this. Let us say I am looking from the top. This here is your sample in a cuvette, all right. Excite using pulsed light. Fluorescence goes out, right. Now, let me try to draw it in this way. Let us say I have some magical power whereby I can see the photons along this line with very great time accuracy. What will I see? Suppose I can make out between photons that arrive first and photons that arrive later. Initially, the first photon will reach, right. Go back to your analogy of marathon runners. The winners will reach first, then the slower ones will reach a little later, okay. And then the photons that have been emitted even later. When I say slower, I do not mean the photons are running slower, I mean they have been emitted at a longer time post excitation, okay. So, suppose I could look at this entire region, then what, and I could see photons, then I would see a distribution like this, is not it? This is space, but photons that have been emitted first would have reached here, photons that have been emitted after some time would have reached here, photons that have been emitted even later have reached here, and so on and so forth. So, does this not look like a fluorescence decay? And is that not the histogram that we have been trying to construct all along? Yeah. Do you understand what we are saying? Suppose I have a slit here at this point, then first the photons that have been emitted shortly after excitation will reach, followed by photons that have been emitted a little while later, and so on and so forth. So, this is basically a depiction of the same thing. We have some kind of a slit here, and what arrives there is not a bunch of photons altogether, but a distribution of photons. So, photons in band 3 would go in first. There is a little strange way of drawing it, but then I have taken it from this paper. I would have written 1 first, 2 second, 3 third, but well, we go with whatever is written there. So, photons of band 3 would reach first, followed by photons of band 2, photons of band 1, and the 1, 2, 3 are only 3 of in principle infinite number of bands that I could draw here, okay. So, this is where it reaches, okay. Let us say this is a slit, and here we have input optics, lens or whatever. So, it gets in, and this is the photocathode. What will happen? This band number 3 of photons is going to emit a bunch of electrons, then band number 2 will emit another bunch, band number 1 will emit another bunch, and the number of electrons emitted is going to be proportional to the number of photons in each band, right. So, if I could plot the number of photoelectrons, then they would have the same distribution as the distribution of photons here. Are we clear about that? Right. Now, what happens is, okay, this is the photocathode, this is anode, and this entire thing is inside something called a streak tube. And until now, we have not told you what the meaning of streak is, where does streak come from all of a sudden, we will see shortly. Okay. What happens then is that you use a sort of an oscilloscope kind of arrangement. I think we all have studied how an oscilloscope works in class 11, 12 modern physics. How does an oscilloscope work? What is the first thing that, I am not talking about digital oscilloscopes, of course. How they work is a mystery to me as well, but good old fashioned oscilloscopes, the way they work is, maybe I can draw. First of all, you have an electron gun. An electron gun, something that are very exotic, not very easily found. Yeah, they are not. Yeah, TV is basically an oscilloscope. Instead of seeing curves, you see people and places and pictures and so on and so forth, right. So, basically you have an electron gun in an oscilloscope, and here you have a phosphor screen. So, if nothing else is there, the alignment is said to go and hit the center of the phosphor screen, and you would see one bright spot on the screen at the center maybe, or depending on center, side, wherever. Next, what do you have? You have, let us say, two plates, one above, one below, and these are attached to some high voltage. Let us say this is minus, this is plus. The top plate is negatively charged, top plate is connected to the negative end of the power supply, bottom plate is connected to the positive end. What will happen if I apply a voltage here? This is minus, this is plus. So, there should be a deviation this way, right. So, now instead of hitting the spot at hitting the screen at the center, you would see a spot somewhere below. Look, if I applied a constant voltage. If instead of a constant voltage, I apply an oscillating voltage like this, then what will I see? This is negative, this is positive. First it is 0, then the magnitude of negative voltage goes up. So, this spot will start travelling below, and then it turns back. So, it will turn back and go up as well. Okay. So, it will go up and down. So, what do you see? You see a vertical line. Clear? All of us have studied all this. I am just revising in case we have forgotten. Okay. So, this is what you can see, as sine curve generates a line on the oscilloscope screen. Okay, and that is completely useless, because I cannot really see the curve. The purpose of the oscilloscope is to see the shape of this curve. So, to do that, what you do is you use another set of plates at right angles. So, the initial set of plates was like this, now the plates are like this. Now, what will happen? If I apply a voltage here, and in an oscilloscope, the kind of voltage you apply is a sawtooth voltage. Okay, you start from maybe 0 or some negative value, goes up, 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 and then becomes 0 and comes back here. Now, what will happen? Here, what will happen is this spot itself will be deflected here. Okay. Maybe I will draw like this. Without anything, the spot would have been here. At initial time, along y direction you have applied this signal, along x direction you have applied this, and let us say this is such that this is negative and this is positive. So, what will happen? At 0 time, no displacement along y, and let us say this voltage is such that this spot is displaced here. After some time has passed, what will happen? Along y direction there should be a positive deviation, along x direction there should be a deviation towards the center. So, the spot will move from here to here. So, this way this is always adjusted in a way that this maximum reaches when the spot goes horizontally from here to here. And if you have all the settings right, then you get to see this oscillation. That is how an oscilloscope works. Okay? And that is why it is called an oscilloscope, because you can see oscillations there. So, you need two pairs of plates, one vertical, that is where you apply the signal, and one horizontal, that is where you apply the trigger. Okay? The trigger is always sawtooth. Sometimes you have self triggering, but that also generates a sawtooth signal. Why? The signal is what you want to see. It is not necessary that it will be a sine wave, it can be something else. All right. So, this is how an oscilloscope works. Now, let us get back to this. So, here what you have is, you have these deflection plates, pretty much like what you have in the oscilloscope, and the way it is drawn here, they are top to bottom vertical like this. Okay. The voltage that you apply there looks like an ogive. So, what will happen then? So, this is color coded 1, 2, 3. So, when 3 comes, well, it is done in a little funny manner. What you have to think is that you have to go from here to here, because 3 arrives first. So, remember what is happening, this bunch of photoelectrons 3 goes through the slit at one point of time, bunch of photoelectrons 2 goes in at another point of time later, bunch of photoelectrons 1 goes in at another point of time later. Okay. So, when 3 passes, let us say this is the voltage, then what will happen? 3 will be deflected accordingly. When 2 passes, the way we have drawn it, we are at 0. So, 2 will go straight. When 3 passes, sorry 1 passes, it is on the other side. So, it will go up, all right. So, what are we doing here? We are deflecting, but we are sending photoelectrons that arrive at different time in different directions, right. So, effectively if you go from top to bottom, this direction now denotes time. Let us say this is, of course, this is continuous object unfortunately, but let us say this is your slit. Okay. When this goes in, this part, the initial part, your voltage is such that it goes here. When the middle part goes in through the slit, the voltage is such that it will go straight. When the end goes in through the slit, the voltage is such that it will go up. So, what is happening? Photons arriving at this slit at different times are sent in different directions. So, what do you get? Suppose now you put an MCP here, and after that you put a phosphor screen. What is the role of MCP? Simply to increase the number, you remember 1 to 40,000, increase the number of photoelectrons. What are you going to see on the phosphor screen? You are going to see a streak. 1 is a point, 2 is another point, 3 is another point. This you understand, right? How bright will this spot be at 1? How bright will it be at 2? How bright will it be at 3? Depends on number of photoelectrons in the band 1, band 2, band 3. Okay? Understood? So, now it is a phosphor, actually you can see it. If you have a streak camera where this detector part can be opened, with your eyes you can see a streak, an actual streak. And the beauty of this is that in this streak, this line is actually the time axis. Okay. So, you see this shape of photoelectrons, x axis is time. Now, if you do an analysis of the intensity here, you are going to get exactly the same shape, and this axis which is now vertical, that is going to be the time axis. All right. That is how a streak camera works. So, what are we not doing here? This MCP, we are not really trying to gate anymore. We are not trying to put a volt. What we did in ICCD to do a time resolved measurement is that we were applying the square pulses of high voltage. We do not do that anymore. MCP is kept at a constant voltage, constant magnification. How do you get time resolution? By sweeping this voltage here on the deflection plates, and in fact, this can be done much easily with much greater time resolution. That is why a streak camera gives you much better time resolution than a gated ICCD detector. In fact, with streak camera, one can go down to, one can measure almost up to 1 picosecond lifetimes. Okay. Is there any question so far? Have we understood how a streak camera works? Yeah? You get a streak. Have you understood streak business? Basically, you get a streak on this phosphor, and then you capture that image and do an analysis. What is the intensity at every point of that streak? You get a plot of that, that gives you the decay. All right. So, now once again this phosphor screen is a square, not such a big square, typically of this size. We are only using one axis here, the other side is wasted. Can we make use of both the dimensions in streak camera? Actually you can. This is one way of doing it. I hope you can see the projection. So, this is your pulse excitation, this here is the cuvette where your sample is, you collect and then it goes to a grating. This is not a monochromator, again this is taken from this paper by Komura and Ito. This is again a spectrograph basically, this exit slit is not there. So, you disperse, all right. Now, see along x axis you have dispersed, right, you have got the spectrum. Along y axis you are applying voltage, so you are getting time. So, what will you get on the phosphor screen now? You are not going to get one streak, you are going to get an image, right. And I will show you an example here. Just look at this image first, then we will say what it is. Here you see this axis is wavelength, remember we had dispersed by using a grating, a spectrograph. This axis is time. So, if you go from left to right, you see in case you cannot read, I will read it for you. I mean in case you cannot read what is written here, I do not doubt the level of literacy, but it is really blurred. I can read it only because I know what is written. 400, 500, 600, 700 nanometer. From left to right you see this is the spectrum. From top to bottom, what is this? This is time. So, you can see actually it is a rise and then it is flat, and times that are there are, problem is I also cannot read what is written there, picosecond or nanosecond. I can read 0, 1, 2, 3. I cannot read whether this one is picosecond or nanosecond, I think nanosecond. Okay. So, this is how you can actually use the entire surface of a 2D detector to generate time resolved emission spectra or time resolved spectra. Okay. And lest I give you the idea that this is useful only for fluorescence experiments, because you can read about streak camera from Lakovich's book. But the reason why I chose this figure, there is a book, a manual on streak camera, I can share it with you, this, from Hamamatsu. This is a book, Guide to Streak Cameras. Okay. It is freely downloadable, you can download from the net. I took the picture from there. This is not time evolution of emission spectra. If you look at this setup and you can make out what is there, here you have Nd:YAG laser, then this is third harmonic generator. So, you generate omega, well omega is already there, 2 omega, 3 omega, then you disperse them, 3 omega comes here, then here, here, this is where your sample is. Okay, 3 omega, 355 nanometer pulses are exciting the sample. Then omega goes here to this XC tube, generates white light. White light goes back to this. You see, on this sample, you have a pump beam and a probe beam. So, what you see here is actually transient absorption. So, nowadays for nanosecond, microsecond time domain, this has become a more popular technique than using just MCPPN, because you can see time resolved emission spectra, and if you use a short enough pulse, you do not have to worry about deconvolution or any such thing. So, this becomes very useful. Okay. So, you can use both the axes. Okay. And this is not all. You can think of doing something else, and that is also possible. Somebody tried it, somebody I know, but then that somehow did not work for them. I just draw you a schematic to show the other application that might be there. What were we saying? We said that the electron beam gets through, okay. You have these plates, right, and you are applying this kind of a voltage. So, from here you are generating the streak, okay. And then what I showed you earlier is that even before electrons are generated, light itself is dispersed. So, this is one thing you could do. The other thing you could do is that suppose you want to look at some kind of a reaction, then you can again like oscilloscope have two plates, one horizontal, one vertical, and this can be the fast time axis, this can be the slow time axis, meaning you apply a voltage here that gives you the dispersion in say picosecond or nanosecond or whatever it is. In the slow time axis, let us say you apply a similar voltage, but in microsecond or millisecond. Then what will happen? You see decays at different time. Suppose there is a reaction going on, and as a result of a reaction, some new product is formed which has a different lifetime, and you want to follow the kinetics of the reaction using lifetime. Suppose there is protein folding, unfolding, okay? Protein unfolding, and so whatever fluorophore it is, its lifetime becomes small over time, and you want to follow it in milliseconds. What you can do is this one getting one streak can be done in a matter of microseconds. So, in few microseconds you get one streak, and then you apply this voltage on the other axis, the second streak comes say above the first streak, and the difference between this streak and this streak is say 10 millisecond or something, or 10 millisecond is too much, maybe 100 microsecond. Understand what I am saying? In 1 microsecond I get one streak, that gives me the decay at certain delay. Then I apply a voltage on the other side. So, next streak that will come above or below, whatever it is, let us say above. This one comes say 100 microseconds later. So, if there is any change in the decay that occurs in these 100 microseconds, you are going to see it. So, you can actually try to follow a reaction by using a fast time axis and a slow time axis. But as far as I know, the lab where I know this was tried out, somehow it did not work out, but that might have been for some very different reason. So, what we have discussed in this almost double the usual time module today is that we have discussed how one can use two-dimensional detectors to make the most of measurements. But then I am sure I have drawn a very rosy picture of streak cameras to you in the last 50 minutes. Let us end with a discussion of pros and cons. Nothing in this, I mean, there is no free lunch, right? So, what is good about streak camera, what is bad? What is good is obvious, right? You can get fast measurement along two axes. What is bad? Well, in early streak cameras, dynamic range used to be quite poor. Dynamic range means the ratio between the largest and the smallest quantity you can measure. So, if you had a bi-exponential decay, streak cameras were not all that good. But now you can run streak cameras in many different modes. I encourage you to read this book, Guide to Streak Cameras, and there you can see how a streak camera can be run in photon counting mode and so on and so forth. So, now time resolution is better and one can actually believe multi-exponential decays on a streak camera also. Achha, another advantage I forgot before I go into the cons. In comparison with TCSPC, what is it that contributes to TCSPC? TCSPC full width half max of instrument response function, laser width, response time, and well, response time of the instrument, you can say detector and instrument. Here that is not the case, because you are applying a voltage, right. So, you can just use the laser pulse to deconvolute, that is one good thing. Now, coming back to the cons, earlier you had to do this experiment one shot at a time, and if you see my 2002 photochemistry photobiology paper from CAT, there you can see some decay which was recorded on a very not so good streak camera. The streak camera had burnt, actually the MCP had burnt, but we could get some data. you can see that the data quality is nothing like TCSPC. I mean, it's worse than your pump probe data that you get. And that is because it was a one shot experiment. But now with the advent of LabVIEW and all that, most of stick cameras work in synchroscan mode, meaning automatically you record many pieces of data and you do averaging. So, data quality has become much better than before. Why is it that we do not use it? And we have TCSPC, we have upconversion, and that is true for many labs in India. Hardly anybody has a stick camera. Why is that so? Because the cost is forbidding. The cost of stick camera is more or less the same as the cost of your upconversion, and upconversion gives you better time resolution, even though the experiment is more tedious. Here the pro is ease of experiment, quickly you can do things and you can do multiple things as well. Con, at the moment the biggest problem is the cost. So, if that is not an issue, stick camera is a fantastic instrument to get and use. All right. So, that is what it is. We stop here, and then next day we go back to chalkboard a little bit and we start talk about how lasers work, how you generate pulses and so on and so forth.